Okay, well, let's get started. We're going to talk about this article out of the back of Power magazine. And those of you that weren't here that missed the rambling diatribe before this, shame upon you. You can talk to your classmates and they will, I'm sure, enlighten you. Okay, so Jennifer wrote this, and she cites analysis by Intergovernmental Panel on Climate Change and International Energy Agencies, both of which are fairly left-wing organizations, in my opinion. But it shows that achieving a zero carbon energy system by 2050, which is a long-term goal, will require large-scale deployment of carbon capture technology in the electric, power generation, and industrial sectors. So this is talking about carbon capture sequestration. There's all kinds of schemes out there. Some people want to capture that stuff and pump it down into geological, caves and stuff down deep under the ground. But of course, it would never leak back out, I guess. I mean, they're going to pressurize it to get it down there, and they're going to pump a gas, I guess, or they're going to liquefy it. Either way, it's pretty energy intensive. And so, you're going to have a 200 megawatt unit, and you're going to use 125 megawatts to get the carbon buried down under the ground. And I mean, after a while, it seems to me like this is diminishing returns. So, I mean, if we have to do this, maybe there's other alternatives. But like on your articles and, that little research you did about a 2,000 megawatt plant, how many square miles of solar collectors is that? A lot. And you can't do wind in Tennessee because it ain't going to blow. And all of a sudden, if you're going to try to do nuclear, it take you 10 to 15 years to get the license. Another 10 years to build the plant. So, I mean, it's tough. It's tough out there. Okay, commercial scale carbon capture has been deployed for decades in some industries, and commercial scale post-combustion carbon capture retrofits of power plants are operating successfully in the US and Canada. I guess there's been some of this, but to my knowledge, there's not a whole lot of it. It's expensive, it takes a real commitment, and that's where this thing is headed. So let's see let's just go on here. Now the world needs to accelerate and deploy projects across industrial sectors to achieve a critical mass of commercial deployment by 2030, sufficient to reach the economy-wide scale needed to meet mid-century decarbonization targets. Economy-wide deployment is possible, yet can only be realized through increased public and private investments. We're going to have to spend a boatload of money to do this. And who's going to pay for it? You say, oh, well, the government will pay for it. Well, okay, so they're either going to just write a check and it's going to go on the national debt calculator. Have I shown y'all the national debt calculator in here this year? Oh, we may have to do that today too. Okay. Or if the power industry has to pay for this, you know where it's going to come from. It's going to come from the ratepayers because they got no place else to get money. And so your utility rate, instead, I'm paying 9 cents a kilowatt hour. If they start doing this stuff in a grand scale on TVA, I'm going to be paying twice that. 18 cents a kilowatt hour. I'll really yell at my wife for not turning the lights off. She won't ever turn a light off. She hates the dark. I hate the light at night because I have to pay for it, Anyway, that's just the way it works. So that's what this is getting into. Role of federal policy in increasing U.S. deployment. The primary challenges to carbon capture are not technical, but of public policy and political will. That translates into money, I mean, if it was free, everybody'd vote for it, right? A portfolio of federal policy support comparable to what has fostered the commercialization of other low and zero carbon technologies could reduce uncertainty among investors and project developers about applying carbon capture to specific industries, build out infrastructure, support the expansion of saline geologic storage that means down in the ground, and grow new markets for captured carbon, carbon dioxide, and carbon monoxide. Now, who's the biggest emitter of carbon to the atmosphere in the world? China. And who do we compete with on a global basis? China. Now, some of that's being reshuffled. Not sure, you know, all the stuff in the news. But so if we start doing large-scale deployment of carbon capture and sequestration, what happens to our utility rates? They go up. What happens to our competitive position vis-a-vis China? It goes down. Wage rates are already higher over here. You know, we've got to have some advantage. What happens to jobs for young engineers that come out when we're no longer competitive with the Chinese? Not so good. So these are all complicated and interconnected issues. But the foundation of this goes back to, what do you really think about this climate change argument? It drives me nuts. Bernie Sanders has his own private jet. So he preaches all of this stuff, Green New Deal and all this stuff, and for the last 2 years, he flies in and out of his own little private airport in his own private jet. Well, that's not green. Al Gore, who makes $150 million a year on this stuff, making videos about how Miami's already underwater. He's got his own little private jet. He lives in a, 15,000 square foot house in California, and he's got multiple houses around the country. I mean, is that green? What do you think green about that? So, you know, I mean, I don't know. But, you know, I don't know. It's kind of like, there's a quote out there. Who said this? I forget who said this now, but it's like, when everybody thinks the same way, nobody thinks very much. You know, when everybody's 90-something% of the people are all lining up on the same side of an argument, I start getting skeptical, like, I don't know about this, especially when it's something like this. That, anyway, so that's enough. I don't want to do this tirade forever. You guys probably enjoy it more than the other, but anyway, so just read through this, and you can, if you want to incorporate a little of this in this little position paper you write, that's fine. You got plenty of time to do it. Okay, comments?
I find it funny that she's trying to say that it's not a technical issue and that it's just a political one, because okay, that's pretty much the opposite of what I think on the problem.
On carbon capture?
Yeah, but she's saying it's not technical.
Well, I know there have been some pilot projects, but I'm not, and I must say, I'm probably not up to the latest on this, but I mean, there's not been widespread. Now, in some industries, you know, some companies may be recovering some of this in order to produce a carbon-based product that then they can sell. I mean, you know, if that's free enterprise doing it because there's a market for it, go for it, man.
I mean, that's where a lot of the argument is. It's just the technical side of it. Whereas, don't try forcing a lot of this kind of stuff onto the public at their taxpayer dollar.
Yeah. Well, you know, back during the Obama administration, what they supported some of the solar. What's the solar company? They dumped $500 million in, and then it lasted another 6 months, and then went belly up. Solyndra? Yeah, it was Solyndra. And then there was the, what's the one up in Clarksville that had some government support? Oh, There's one up in Clarksville that was producing solar panels, and I think they've shut down production because they couldn't compete. But see, now part of that could go back to what Trump's trying to do with tariffs and that sort of thing to level the playing field. If he puts tariffs on Chinese solar collectors, then some of the American companies may become more competitive. I don't know. Each one of these issues is pretty complicated. All right, so we're through that. We did that. Okay, so back to my cryptic notes. I know you love these. I do too. I wanted to say a few more comments here. I kind of went through the flue gas stuff. Oh yes, and I have an animation or two for you. So let's start. We'll just go through some of these topics. For SO2, scrubbers with limestone. Okay, let me show you this. This actually, they may show us this. This comes from TVA, but this is an animation of what a utility-sized scrubber looks like. This is pretty cool. So there's two different configurations. This one, you see the gas coming in the side and turning up. That is water with limestone dissolved in it. So calcium and SO2 form CaSO4, which is a solid, okay? And so then the solid you have to continually pull out of the water down in the bottom of this. But so they keep feeding limestone into this, and then it's basically a spray wash. And those are the dirty flue gases coming in this configuration. They come in the top and they get cleaned by all of the water sprays. And of course, look at all these pumps over here. I mean, you got a whole row of pumps. There's several thousand horsepower of pumps operating. And see, that's additional plant load, parasitic load that it takes to make these things operate. And if you make the trip to Kingston, they have, I don't know what configuration, you can't hardly see, you just see a big box from the outside and they show you the video. But you can go down and you can see the pumps and all the stuff that have to operate to make this work. But then, they pull that CaSO4 out of that water bath, and then that becomes a product that I think is saleable, So that sulfur and that calcium can be recycled, like wallboard and stuff like that. It can be mixed in with that, I believe. So that's how a power plant cleans up the dirty, nasty sulfur and I mean, it's pulling other stuff out of there. When you spray all that water in there, you're going to pull particulates out, and I'm sure they pulls out some mercury and some other stuff. But it's primarily designed for the to remove the sulfur. So that's cool. All right, and I got another one here we'll get to in a minute. So that's it. Now on the NOx, and you'll get a detailed chapter on this later, but I mean, some of this kind of fundamental stuff I want to make sure that you get. There's really two sources or two mechanisms by which power plants produce NOx, which is oxides of nitrogen. So NOx, one would be thermal, and two is fuel. Okay. If you look at over here on the side in my scribbling, you see an ultimate analysis of coal. So this is, you send it to the laboratory and they tell you on a percent mass basis what's in it. Well, you see, we've got to 1.5% nitrogen N2 is bound up in this coal. And so when you burn that coal, guess what? That N2 has the potential, I mean, some of it could get released, but it has the potential to burn into NOx. Okay, so that's fuel NOx. So, you know, nitrogen bound up in the fuel, when it goes through combustion, some of it gets converted over to NO, NO2, NO3, the family that's kind of called NOx goes up the stack. Okay, that's one. What do you think thermal NOx? What's another source of nitrogen in the combustion process? Air. We got to have oxygen, and we sure are too cheap to buy bottles of it. It's free, right? Problem is, it's what, 21%. So good, 21%. And it's basically 79%. There's got a few trace gases. That CO2, you guys quit exhaling. Would you quit exhaling? You are polluting my atmosphere. I love saying that. I don't know why. So obnoxious. Anyway, but basically 79% of what I breathe in is nitrogen. So we got to get oxygen for combustion. We're getting all that nitrogen come in with it. So, okay, let me show you a picture of the fireball. This is show and tell day. They told us to be super nice to you guys. This is as nice as I get. I want you to know. If you don't consider this as nice, I'm sorry. I'm out of business. No, that's the scrubber. Sorry. Dummy. This is Kingston. That's down at the bottom of the boiler. That's my favorite view. They got a door. You go down in the basement, and you open the door, and you walk up on this little platform, and you look up. Well, this is what they call clinkers and stuff that has attached to the boiler tubes that's fallen down. And sometimes they try to keep a little water down there on the bottom so that stuff will kind of quench out. But that's looking up. That's the fireball that's up above. So this boiler is probably, I don't know, 100 foot tall, something like that. And so we're down at the bottom looking up. And you got these burners shooting coal and air out into this fireball, which is probably swirling around a little bit. And you see the walls over here are lined with tubes. We'll look at that again. This whole furnace is lined with, say you see tubes down through here. This is called the nose of the boiler. And then it goes up, and it's pretty much a rectangular cross section up above this where the fireball is. But all of this enclosure is lined with tubes, and that's where the steam is generated. So we have a mixture. Well, we have water comes out of the steam drum that gets sent to the bottom of the boiler, and then it spreads out into headers that feed all of these individual tubes. And so you have water circulating through these tubes, and that's what keeps the boiler from melting. Because, I mean, look, those tubes, if you don't have circulation, water flowing through those tubes, you're going to have a pile of molten metal pretty quick, because this is 2,500, 3,000 degrees. That's hot enough to melt steel. Okay? So, well, no, it's all, the entire furnace is enclosed with tubes. And I was looking for some pictures. That's Mike Coffey's hand. He was a Tennessee Tech guy. He's sitting there talking, but for some reason, I guess I'm, wow. All you really hear is the roar. But so if you make the trip, that's always make sure that we go down there, but there you go. That's the fireball up above you. And let's see if we get a good shot of the tubes. I think this is somebody, Jackie Sherrill, put this together for me on his cell phone. I've got some others, but he did a better job than I usually do. Get back over there. I hit the button. There you go. You can see those tubes right there. And they get, they collect ash. They get deposits on them all the way through. And this is the furnace section, we'll see. So the heat is released in here. The steam is generated in those tubes. The steam goes to the drum where it's separated, and then it goes back to the boiler, back into the convection pass where it is superheated, where the reheaters are. We've got multiple different heat transfer sections in this boiler, okay? But these are the furnace tubes, called water wall. Those are the water wall tubes where the steam is generated, okay? And we have what's called, so see this opening? It has openings ever so often. So they can put a soot blower lance. They have soot blowers at different levels, and they can roll these things in while this thing is operating, and it blows either high pressure, it can be high pressure water, it can be low pressure steam. You can use acoustic horns, different ways to knock the ash and the soot off of those tubes. So they can clean the entire furnace with different combinations of soot blowers. On any sort of a solid fuel boiler, you have to be able to clean the heat transfer surfaces. What's that? Yeah, while it's operating. They do it online. And if you're looking at the stack, all of a sudden you see this kind of big change of, they're blowing soot, you know? And so the emissions change when they're doing that. I'm sure the precipitator gets really loaded and all that sort of thing. And it costs them money because they're gonna blow. If they're blowing water, they're blowing, you know, pretty warm water because you can't shock these tubes; they're so hot. So that's water that you have to make up in the system. If you're blowing steam, that's steam that didn't go through a turbine, and so there is a economic cost associated with soot blowing. Years ago, there was a guy here, Bob Smoke, that had worked at Babcock and Wilcox, the people that produced the book and, you know, a lot of the stuff we talk about here. He was a real boiler guy. We had a project at Gallatin, neural net control of soot blowing, optimal soot blowing control. So considering the efficiency effects and the cost of soot blowing, you know, and it's complicated because you have different sections of the boiler, and they take different, they take pressure readings, you know, because as the dirtier it gets, the harder you got to run the fans to push the gases through. So you can tell based on the different pressure drops what section, and also temperatures, that the operators can tell what section's getting dirty. The question is, at what point is it economic to actually blow soot? If you blow soot too often, you're just wasting money. If you don't blow soot enough, you can slag up your boiler. And I mean, if it gets bad enough, you have to shut down and go in with jackhammers and jackhammer this stuff out of there. Because a lot of this, I mean, this stuff is like molten rock. You know, that's what the ash is. It's inorganic stuff, basically rock particles. And some of it, you know, and it depends on the coal. Some of it will have fusion temperatures that are low, some of it medium, and some of it high. Because you dig this rock out of the ground, and Lord knows it's got all kinds of stuff in it. So, you know, you have a speck on it, but you know, it's just, you know, you just can't tell that much, you know. So, I mean, the operators get a pretty good handle about, hey, that last load of coal we got in here, that stuff is slagging up like crazy. We got to be really careful. Or you say, wow, that load is really good. I don't have to blow soot nearly as much. And say that's the online day-to-day stuff of operating one of these units. Okay, so that's your water wall tubes. I love it. Man, if you wanted to get rid of a corpse or something, man, just toss it up in there, right? Anyway, not that we would ever be wanting to do that. Okay, all right, so let's stay on this. So thermal NOx, after seeing that fireball, knowing that we've got all this nitrogen going through that system, what do you think thermal NOx is? Anybody want to hazard a guess? What's disassociation besides when you unfriend somebody on Facebook? Yeah, it's when an N2 decides, enough, enough, I can't stand you anymore. We're splitting. And they become an N and an N. Well, an N2 is pretty inert. It doesn't want to, it's a happy couple, But an N by itself is looking for companionship, out making the Friday night bar scene, And if that N meets up with an unsavory character, like, I mean, I don't want to mention any names, but, all of a sudden, instead of getting an N squared, an N2, you get an NO. And you can't take them home to meet mama, right? Because those O's, man, an N can't bring an O home. It could be worse, you could get an O2. Or it could be worse, it could be an O3. Now, that's a little kinky. But, anyway, so that's what's called thermal NOx. You take this stuff, and the higher the temperature, the more this stuff will disassociate. I don't know, back when you did combustion stuff, did you do that in thermal disassociation reactions? Oh, there's reaction, when you do the reaction constants and all that stuff, you can predict, if you have the reaction constant and the enthalpy of formation and do all that good stuff, you can predict the amount of disassociation as a function of absolute temperature and all that. But anyway, as far as we're concerned at this level, the higher the temperature you get, if you go up another 10 or 15 degrees or 100 degrees, you get a lot more disassociation. And so the low NOx burners, what they try to do is stage the air. Say they don't put all of the air in at once because they want to keep the fireball cool. So, you're kind of, this combustion is tough stuff, because the hotter you get it, the better it burns, the better burnout you get on the carbon, but the more NOx you produce. And so if you stage the combustion, the primary air comes in with the coal through the coal pipes, and then you have secondary airports as you go further up in the boiler. That puts more oxygen in, but you don't want to throw it all in at once or the flame temperature will go through the roof and you'll make NOx, you'll just overwhelm yourself. And so that, stage combustion, controlling that temperature, and that's going to reduce the thermal NOx. That's probably not going to do a whole lot for the fuel NOx, because where that fuel is burning in that fireball, it's still pretty darn hot, So anyway, that's kind of the story on the NOx generation. Okay, and just kind of FYI, as I go through these, in the old days, I would write all this up there. And if I didn't have, this room is hard. And so as we go through these detailed discussions, this is stuff you're going to be tested on. I may write it, I may say it, but feel free to slow me down. And if I'm going too fast for you to take notes, just say, slow down. Yes, ma'am. Yes, sir.
Would you possibly send these out to us, these notes? Or?
Do you want a copy of that?
Just maybe reference. So I don't have to sit here.
I don't care. I don't care. They're ugly, man. These things have been around a long time, and I just scribble stuff all over it. Because, when they're written and amended for me to write all this stuff on the board. But that's kind of what we're not doing anymore. And I can't really do it in here. I just think, well, I guess I could, but I've kind of moved on, Okay, ultimate analysis. This is one of there's two analyses that get done on coal. As far as the combustion properties like this. There's lots of different tests. If you look in the Steam book or online, there's ash fusion tests. There's there's probably 10 different coal characterization tests, and there's ASTM standards on all of that. And the guys that purchase coal, they're on top of all of that in order to make sure that they put out the right specs for the coal that they want for their boilers. Okay, and because there's different types. There's anthracite, there's bituminous, there's subbituminous, and there's more than that. So the world of coal is very complicated. Okay, so there's ultimate and then there's proximate analysis. And I didn't have anything written up in this part of these notes about it, so I searched this up. And I can send this out. This is actually a test. There's kind of a little test protocol here. I had not seen some of this stuff before, but this is, you know, in the laboratory, proximate analysis of coal. And there, I mean, there's more here than we need to know. But so what they determine from this is they determine moisture, volatile matter, which is, I think, essentially the hydrocarbon gases that can be driven off and burned like almost instantly. Then there's the fixed carbon, the solid materials in there that'll burn. And then there's the ash, okay? And so that's what a proximate analysis is. That other list of all the different elements, I'll put it back up there in a second, is the ultimate analysis. Okay, but this is kind of interesting. I had not seen this before. So what they do, apparently, and I had some idea in general, but I had not seen the fact. So what they do is they take a certain amount of this, they grind it up, and they heat it up for a while. And initially they heat it up, I guess, in a nitrogen environment, so nothing will oxidize. That makes sense, okay? So you can see it starts out over here at 100, and then after a certain length of time, I guess 25, whatever minutes, you see how this goes down a little bit? So some of this, initially it's moisture loss, and then that's the volatile matter coming out. That's those hydrocarbon gases coming out. And then they switch to air at high enough temperature. See, this is, 900 degrees C. That's going to burn. That's pretty warm. And then they burn it. And so that's the fixed carbon determination until this comes down. And what's left is ash. So, I mean, it kind of makes sense. But anyway, so that's approximate analysis. And for the ultimate analysis, I'm sure it's got to be much more complicated. Yes?
So, like, do they get like one type of coal from a certain region and another type from another region, or can they, like, one mine produce both types or multiple types?
No, they get it in different regions. And in fact, TVA now, at least last year, the last couple of years we've been up there, they're blending. There's PRB, Powder River Basin coal from out, I think it's Wyoming, Montana, out there. That's a big coal producing area. That's more of a low sulfur, high ash, low BTU. It's not great BTU content, but it doesn't have a lot of sulfur and it does have a lot of ash. And they're blending that with some, I think, bituminous or subbituminous from maybe Kentucky, Pennsylvania, West Virginia, something like that. And they're doing roughly a 50-50 blend. And see, that's complicated because they've derated the number of BTUs they're putting in, but they do it for the emissions. The emissions rules the roost. Whatever all their basic decisions, the first thing they consider is emissions. What can we do to better control emissions? And then say, well, that's going to be a hit on heat rate or efficiency. Too bad. Heat rate's not in first place anymore. It's emissions. So we've got ultimate analysis and proximate analysis. And there's the, and I mean, if you want to learn more, I mean, just Google ultimate analysis coal and you'll find up to things will jump up in your face. Okay. Okay, tube spacing. So we talked about different fuels. So now that you've seen the boiler tubes, if a boiler is designed for coal, now the tube spacing in the furnace they're pretty tight. They're like, if I look in that coal generating portion of the furnace, if I take a cross section, I've got my structural, I've got steel and back, but all of these tubes are basically right beside each other all the way around. And after a while you get tired of drawing these little circles, but they go all the way around like that. And then that water's coming up and that fireball's in here, and some of that liquid is being boiled off into steam, and then we separate that out up at the top. We'll talk more about that. when you get up to other portions of the boiler, and here, let me see, that's why I give you some of these. I'm not sure which one's the best. This is pretty good. Yeah, okay. So here's your furnace water wall tubes over here, your fireball, your burners, and all that stuff. And the gases come up to the top of the boiler. There's the steam drum. And then they turn sideways, and then they go across all of these heat exchangers. Okay, and then the steam so this mixture goes back to the drum, and we separate out the steam, and then the steam flows back to these various heat exchangers and picks up additional temperature. So that's where the superheating occurs. So the spacing on these, so these are just heat exchangers that are in the gas pass, and the gas has to pass over there. Well, if you're designing a boiler for coal, you have to leave more passages, you know, more spacing, because this is going to foul up. You know, you're going to get ash, and you have to accommodate that, and you got to be able to spray that stuff and get it out of there, you know, to keep it clean. If you're designing for natural gas, you can pack those tubes together because there's not hardly anything to sit up, to plate out on them on the outside. So your tube spacing and all of that in a boiler is dependent upon the fuel that it's intended to burn. Get it. So that's what the comment here about tube spacing, unit size for the same steam production rate. The natural gas boiler is going to be far smaller. You don't have all the fuel handling issues. You don't have to space the tubes as far apart and all of that. And of course that then relates to the expense of the boiler. How much are you going to have to pay for this thing on the front end? Oh, gas fire, yeah, smaller footprint. For natural gas, it's pretty much NOx is your only real pollutant. Okay, when burning coal, this is LOI, is a power industry term you need to know. So, periodically on a coal boiler, this should be done, I don't know, I'd say probably every 2 months or something like that. I would recommend. I'm not sure what TVA does. You go to the ash pile and you take samples, and there's an ASTM standard on how to sample an ash pile. You can't just go out and grab a little cup here. You got to go certain places and certain depths and all this. But anyway, you get your ash sample, you send it to the laboratory, and they tell you how much carbon is in the ash. Now, what do you think about carbon in the ash? Is that a good thing? That's fuel that you bought that you didn't burn. So carbon in ash, the power plant term is LOI. Basically, it means amount of unburned in the ash. Of course, you can, I mean, for any solid fuel boiler that produces an ash, this is something you would want to be concerned about. You would want to track this. I mean, even if you had a big wood boiler, there's burning waste wood, you would still want to know, well, how much carbon do I have left over? And from this month to next month, you know, for the last 5 years, how has this changed? You know, if all of a sudden this jumps up, then you've got an issue someplace because you're not effectively burning your fuel, okay? The TVA, anybody want to venture a guess? What would be the first thing you would look at if this increases? That's possible, but that's not first. No. That's not what I'm thinking of. That might have some impact on it.
What's the question again?
The what?
What's the question again?
What's the first piece of equipment you'd look at if this LOI number spikes up? Nope. Nope. What's the consistency of the coal that they burn? Face powder. How do they make it like face powder? Ah. What happens if the particle size gets too big? You can't burn all of the fixed carbon. The pulverizer. And what's probably the most maintenance intensive item in the plant? The pulverizer. It's on the hit list. So oftentimes what happens is, because they're always crushing that coal, they wear. They glue these little ceramic discs. Looks like a mosaic. It's like a hexagonal disc, and they fit them in there, some sort of a metal matrix that holds them in, and that's the surface, because that ceramic that's about as hard as you can get, and they still wear, and the clearances open up, and then the particles become larger than they should be, and you can't burn all the carbon out, and so it winds up in the ash. So that's probably number one. Now, all of these other things everybody suggested are very good. And you guys were thinking about the combustion process. But if the coal particle gets out of spec on the large side, even the combustion process can be perfect, and it doesn't have the residence time in the furnace to burn all of the carbon. And so it's just, winds up in the ash. Okay, good. Okay, LOI, large furnaces, the additional components. Okay, this is kind of interesting. Comment, I don't have figure 11, but I got the steam tables here. What is HFG? This is good for the test. This is, huh?
It's the enthalpy of the gas minus enthalpy of the saturated vapor.
That's right. So that's the enthalpy of vaporization. So if we look on the OTS diagram, so it's the enthalpy here. It's this one, HV minus HL. And of course, the thermal book calls it FG. Well, hell, subscript here, subscript there, use whatever subscript you want. So, and I don't know if you've ever thought about this, but let's see here. Boiler side, thermal tables. Just to illustrate, this is the pressure table, and here is HFG, and here's increasing pressure. Wow, look at that. Kingston runs about 1,800 pounds. Oh, I'll get up there too far there. It's that one. At 1,800 pounds, HFG is 502. At 200 pounds, it's 843.7. Amount of energy it takes to go across the dome. So that dome is getting narrower as you go up. So relatively speaking, you need less heat transfer in the steam generation area as your pressure goes. Well, if you go above supercritical, you don't need any, right? Because you don't have, supercritical is up here. And you don't even go across the dome. So, I mean, that's what's happening. This dome is getting skinnier. But, it's interesting. So if I condense a pound of steam, what if I did it at Tennessee Tech? Probably, well, when it comes over here and actually heats water, it's probably 30 pounds. It's probably, let's say 50 pounds absolute. Okay, so it's 50 pounds absolute, we get 924 BTUs per pound. If you take steam at, say, 1,000 PSI and condense it, you only get 650 BTUs to condense it. Now, you get it at 544 degrees, which may be an issue for you. Over here at 50, we get it at 281 degrees. Isn't that funny how world works? At low pressure, you get a boatload of it, but it's at low temperature. At high pressure, you don't get so much, but it's at a really high temperature. So, see, that's why people will want that their steam pressure to be as low as possible. That will give them the temperature they need. Interesting. And so, you know, another thing that we could think about, I thought about doing a calculation. We could, you know, let's say you're running, you know, let's say you got 100 GPM going, say going to your feed water heaters at, I don't know, 200 degrees, something like that. But you're operating your boiler at 1800 PSI. So that means that before you can start vaporizing, you have to get to 621 degrees. So look at how much energy it's going to take just to heat the water. So see, that's what the feed water heaters do. See, that's why we do that regeneration, because say, you know, when we first get back in the steam cycle, we're probably, you know, I don't know, you got condensate coming back, but that condensate, you know, is probably 110, 115, you know, maybe we start at 120, 125 degrees, but we got to get to 6. At Kingston, they got to get to 621 before they can start making steam. And so guess what? That's what those feed water heaters do. They boost that temperature before it, you know, maybe we can get it up to 400 degrees before we go in the boiler. And then thermodynamic theory tells us that helps our efficiency. So anyway. Okay.
Like a startup, it's just everything just driven by the boiler. Like the boiler has to get hot before everything else.
Yeah, they'll fire either with natural gas or fuel oil until they get the boiler. Yeah, because you can't start up on coal. Say they have Lances and they've got some, I think Kingston uses oil, probably diesel, probably number 2. Diesel's number 2. And so they'll fire the boiler and they got to get it up to a certain point before it can sustain. Because when you spray those coal particles out there, it's got to be hot enough so that those things will auto-ignite. You know, it's got to be hot enough that the volatiles come out and that burns, and it's hot enough to go ahead and the carbon starts burning immediately. Or the particles will just kind of hang. Well, you could get an explosion then because you get particle-laden atmosphere and then all of a sudden blow the thing, like a grain silo or something blowing up. Yeah. Yeah, they start up on something else. Okay, so let's see. We talked about small diameter tubes. That's what lines the boiler. And then the other heat exchangers may be slightly different diameters, but a lot of tubes. That's where the steam is generated and the heat is transferred. Okay, so there's actually 2 varieties of boilers. It's kind of like you can get a manual transmission, or you can get an automatic, like your grandmother has, right? You know. I've got a BMW that's got a 6-speed in it, and I'm really partial to it. But anyway. So the drum boiler has a steam drum. The once-through boiler, no steam drum. You don't see as many once-through boilers. They're a little harder to control, and you got to do this just right. So we'll talk about the drum boiler first. So it has a main steam drum. Top of boiler. And we can go back and look at, I think we had a pretty good picture going here. Here, yeah. Okay, so your feed water goes to the drum. Makeup water goes to the drum. It may already be mixed with the feed water, or it may be a separate line. Depends on. All your makeup water goes to the drum, okay? Then it flows by this downcomer down the backside of the boiler down to the bottom, where it hooks into these headers. Headers are very important. Let me see, I got a picture of a header someplace. There we go. This is a header. Now, this particular discussion here is about cracking, which is a bad deal when you start getting header cracking and all. But the idea here is this downcomer would come down to the bottom of the boiler, and then all the individual boiler tubes would stub into this horizontal pipe. And so this water comes down, fills up this thing, and hopefully we feed about an equal amount of water into each one of these tubes down at the bottom of the boiler. Then that water rises up, part of it vaporizes and goes back to the drum, okay? So, and then back at the top of the boiler, there's another header where all of those tubes come into, where that mixture then, well, it could be, or it could be the individual tubes go to the drum, or you could have a header that accumulates that flow, and then you took the single flow back to the drum. It depends on the design. Some drums are big, and the individual tubes will stub directly into the drum. So you can have it both ways. But when you hear header, what needs to pop up in your mind is a picture like this, that I have a central pipe that can be feeding flow into this to feed these individual tubes, or it could be the flip side. All these individual tubes are feeding into here that then feeds this. And so I'm either putting together all of these individual flows and taking that up here, or I'm going the other way. I'm coming in and I'm spreading out that into these individual tubes. But, you know, I mean, it's a fairly simple idea, but it's critical to the operation. So we've got to have these headers to be able to work with all of the tubes that we've got in the boiler. Okay. So I think we've pretty well described this. We come down in the downcomers, and we eventually get to the bottom of the boiler, and we feed. It's hard to see exactly where they're bringing this. There's downcomers. Anyway, it feeds into all of these individual tubes. Okay, so let's write some of this. So what are some functions of the steam drum? Well, we have, it receives feed water / makeup water. That's one thing. You can do chemical addition into a steam drum or into a line that feeds into a steam drum. So it can facilitate chemical addition. We have the steam separators are in the drum that separate out the steam from the returning feed water. So the steam separators are in the drum. And the fourth is that it holds a reservoir of water at the top of the boiler to make sure that these tubes don't go dry. If those tubes go dry, you've got a fireball, you got a big problem. It doesn't take long. You'll over temperature the tubes, you'll damage them. If it goes on too long, you can start melting them. And so that's a pretty important function. So.
Have you ever seen melted tubes?
Well, you know, I used to have some that had that were blown out. I mean, if you go to the plant, they probably should have got a closet someplace where they've got a bunch of their old failed boiler tubes. Where they've split open, or they've had erosion, or had all kinds of different issues. But so a failed boiler tube is pretty common. Now, one that actually melts, I think, is probably not common, but ones that go over temperature, and then it changes the material properties, and then either fatigue failure or erosion, they fail more quickly. I think that's pretty common. Hold reservoir of water at top of boiler. I don't know, can you all see over the, maybe not. It's interesting. You talk to the boiler guys and they're concerned about the condition of their boiler. What they care about is keeping all of the temperatures in the proper range. And we do that by keeping, it's the mass flows through all of the tubes that cool them. Because you're dealing with gases that are far too hot to put across a tube that doesn't have flow. So that's kind of, so the boiler guy, he would say the most important thing, probably the most important measurement in the plant is drum level. And it's in the, you know, there's a couple other, you don't want to blow something up, you know, and this, that, and the other, but drum level is an extremely important measurement. Yeah, it's possible to inject. Sometimes you'll have a chemical feed into a feed water line, or it can even go into the drum too. Usually it's some kind of oxygen control. At these pressures, they probably don't do much of that. But in industrial type boilers at lower pressures, they don't necessarily have the reverse osmosis and the really top of the line water treatment that a power industry's got to have. I don't know if we've said this, but as your boiler pressure goes up, your boiler water quality has to go up as well. So when you're running 1,800 to 2,400 pounds, you got to have like awfully good water. You know, Tennessee Tech, they're running 100 pounds. They've got a couple softeners, add a little bit of chemical addition. No big deal. But TVA, they're going to be doing reverse osmosis. It's like you have these membranes and you generate a pretty high pressure, I don't know, 400 or 500 pounds, and it forces the water through the membranes and it strips out just about everything. You know, I'm sure there's a few things. I don't know what gets through RO, not much. It's pretty darn good. And they do, you know, when you're up at these pressures, you really don't have a choice, because the higher the pressure, the more likely it is to scale out on the inside of the heat transfer surfaces. And you can't live with that. What was I going to write up here? Forgot what I was going to write now. Well, it may come back. Yeah, 5 minutes.
If a tube fails, is it like common to, what do? You block the end of it up, so.
Well, what will typically happen, of course, it depends where it is. And it depends, it could be spray. If it's in the water walls, it's spraying water steam mixture at high pressure, 1,800 pounds pressure. And if it goes sideways at all, hits another tube, it'll cut that tube. And so sometimes if it's the proper angle, they have to take the boiler offline. They can live with, a small amount of leakage, and I don't know what they consider the threshold at which they have to cut down. But if you have a few small leaks and they're not cutting other tubes, then you're probably okay to run. But if that thing comes out at an angle, it's like a little pinhole, a jet or something, and hits a neighboring tube, it'll cut a hole in that tube, and then that one cuts another one, and pretty soon you just got a big lake and you're done.
I was gonna ask that.
Okay, very good. Okay. Let's see, anything else on that drum? I'd say that's probably most of it. But, it's important to realize that having this water level, where's the drum? You can't see. Well, that's a different picture. I'm changing pictures on you there. Having a water level up here. Oh, I was going to write up there about drum level being an important control parameter. And so the operator always keeps an eye on that drum level. If that drum level goes down too much, or if the rate of change of drum level decreases too much, it indicates that there may be a leak, and they have to be very careful to go ahead and come down if it looks like they're going to run out of water. So.
What about blowdown, Dr. Cunningham? Is that where the blowdown comes from?
Yep. Yeah, that's good. I should put that up there. Drum level is a critical measurement, I guess, for operators to watch. Yeah, and we'll put number 5 up here. Blow down can come from drum. Normally, on smaller systems, but utility designers will pull all kinds of different tricks. But in general, that's what you're doing, is you're blowing down water out of that drum to control the dissolved mineral levels. That's good.
But never all of it, just some portion of it. Like you have to have water in the drum. You're never going to drain the drum.
Oh, no, not you. When you're operating, you have to have water in the drum.
So blowdown is like, it doesn't drain all the water.
Oh, heavens, no. Blowdown is a small, and actually, there's more than one type of blowdown. The blowdown that controls the conductivity is usually a continuous bleed. It's a small continuous bleed, and it will come out of the drum. The lower areas of the boiler, the headers down here, utility boilers don't have a lower drum. Industrial boilers usually have what they call a lower drum down at the bottom of the boiler, and the bottom blow will come out of that. They call it bottom blow down, and it's just done a couple times a day. They'll open a valve and count to 10 or something to blow out any crud that has come off of the inside of the tubes and fallen down. It's an opportunity to drain some of that out of the lower stretches of the boiler. So headers down here at the bottom, they will blow down those headers to make sure that those tubes don't get plugged, that we can continue to feed up through there. Let's see, I think we are just about done here. Let's see. There we go. Yeah, that's a good place to stop. So we'll pick up here next time. You guys have a good weekend. Stay safe. Oh my goodness, please stay safe. And we'll see you on Tuesday for a little exercise, a little mental exercise.